Hi guys, it's your guy Olumide, and today we'll be solving another one of the most commonly asked tech interview question, the insert and search word with wildcards. It's a DSA problem that's commonly asked by top tech companies in tech interview, including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that design and implement a data structure that supports the following operations. The first operation is the insert operation, or we can call it the insert function or insert method, whereby a word will be sent into this function in order to be inserted into the data structure. Right. The second operation we want the data structure to support is the search method. So whereby a word will be sent in into a function and it's going to return true or false, a boolean, based on whether the word is in the trie or not, or is in the data structure or not. So now the word may contain wildcard, which is actually dots. This dot sign is a wildcard, and this wildcard can actually represent any letter. So let's consider some example inputs. We say this inputs, the first one we have is an insert band. Then we have insert rat. So this, we are trying to insert the word band and the word rat into the trie, or into the data structure that we are trying to create. And we are trying to, the next operation we did is the search, whereby we search for RA dots. We see that we are using a wildcard in this word, so which could represent any word. So we are just gonna look at any word that correlates with the with RA dot, not particularly dot, but that dot could represent any other character. So we're gonna search it in the data structure, and if there is a word that starts with RA and end with any other letter, probably ran, probably rat, probably rab, anything at all like that in that pattern, we're gonna search for it in the data structure. We also inserted ran into the data structure. We perform a search, and then for .an, so this time we perform a search for .an, where dot could represent any letter at all. So and then an, so and the output is true, false, and true. So let's see how the explanation for this particular input and output goes. We see that we try to insert band so into the data structure, and therefore the data structure has band. We also try to insert rat nests, according to this input that you can see here. You see rats, you see rats, abi. Okay, when you try to insert rat and our data structure have band and rats, then we try to search for RA dots. So RA dot matches rats in the data structure, so we return true. And we also have B dot dots, so no three letter word starting with B in the data structure. So far all we have in the data structure is band and rats. So, and we see by band is actually 4-letter word. So when we try to search for B dot dot, this is 3-letter, even though the last two could be any other letter or any letter at all. So but because we don't have 3 letters or 3-letter word in our data structure, we're gonna return false, right? Insert ran, so we try to insert ran, and now data structure has band, rats, and ran. And then we try to perform another insertion again, rats. So now it has band. Okay, we already did this previously, right? So whereby it has band and rats. So now we are just trying to search for .an. So and we can see that .an actually matches .an actually matches ran, right? So .an matches ran, so we return true now. And then there's a constraint that's given to us concerning this problem, is that words will only contain lowercase English letter and the wildcard, which is dots characters. We can say that the requirement of this data structure that we are asked to design and implement matches and closely matches that of a trie, because we need to implement the insert word and search word functionality for insertion of word and searching of words. So what we made this data structure and this particular problem unique is that it needs to support wildcard characters. So so it needs to support wildcard characters in searches. And because the insertion in this particular problem actually matched that of a traditional tree, of a traditional trie, we are gonna be using the implementation that we discussed in our previous video. So there's a previous video I did previously on YouTube. It was just the previous video to this particular video. It is the design a trie. So and because this insert and search word have been discussed in details in that previous video, so we won't really be dwelling on these two. So because they actually match that of a traditional trie that we discussed in that previous video, so whereby we insert and populate the trie word by word, just like you can see here. We try to insert band into it, then we try to insert rat into it. So this way we're just inserting word by word. So, and you can go to the previous video for more understanding if you have not checked it. So our focus will be on searching with wildcards, because though in the previous video we also talk about searching just like we talk about inserting, but now then we didn't really focus on wildcards. It's just plain lowercase English characters. But now this problem statement specifies that the words we are trying to search might include wildcard character, which could represent any character, any lowercase English character at all. So now we're going to be considering this particular tree in order to understand what it means to search with wildcards. If we perform a search for the word RA dots, we know we could traverse the nodes R then A, right? You know, in the search for RA dots until we get to this white character now, because after traversing through the node R, which is here, right from the root node, we traverse down here, and then when we get to the dots, and since it is a wildcard, because it's a dot, it could represent any character at all. So if we could have any node that is extending from this node A, which actually represent the end of a word, that is, it has the its word attribute set to true, definitely it could match up for this particular array dot. Why? Because we are searching for a word that begins with R followed by A and ends with a dot, where the dot could actually represent any letter. And if there could be at least a child that extends from A, I mean there's a child of A that extends whether T or N, and has his word set to true, that is, it represents the end of the word, definitely it matches with this particular word that we are trying to search. So we can conclude that in both cases R and T and N matches the condition. Why? Because they both extend as a child of A, so and they could definitely be represented by this wildcard, right? And they have his word set to true, indicating that this is the end of the word we are trying to search, and that means that this pattern arity really exists in our tree node. Sorry, I mean our trie. Now let's say we perform a search for .an, whereby the first character is a wildcard. Since the first character is a wildcard, that means we need to start our search from each child node of in the root, or let me say each child of this root is where we're gonna start our search from, because we don't know, the dot could be a B, it could be a R, or any other direct child of the root, right? And we can do this by recursively calling the search function on each child of the root. So I'm passing in the remainder of the string, which should be an now, into that search function, because now what we're trying to do in essence is that since this dot actually is the very first character in the word that we're trying to search for, so we are going to consider each and every node that are tied to the child node to the root node, right? Because this dot could represent a B or a R, and doing that we have to recursively call the search function, passing in the remainder an. Why? Because by recursively calling tapping into B and R, we already select B at first to be the dot, so you have to pass in an, this an, which is the remainder, to the search function, so it could search the children of B or the child of B. It could search through this remaining part for the remainder an. So similarly, it's gonna do the same for R now, because the dot could be a R. Imagine if it is not a B, it could be a R or any other child node of the root node. So, and we just wanna call the function and recursively pass this particular an into it, so that an will be the remainder that we are looking for. Okay, so now let's pass it into B first. Don't forget, we'll be recursively passing it. We pass it into B, then we pass it into R. We pass it into R, and if there's any other node, we keep on passing it until we see one that actually met this condition. So if we could pass it through each and every node like that, I mean each and every child node of the root node, and we still could not find the one that really matched this, then we can actually return false. So passing the an into B now, you say that's fine. A matches this. A is actually, A will be the next character in the word, because the first character is potentially choosing to be B, and then A will be the next character. And because B is actually or A is actually a child of B, definitely it still correlates. This is BA, so we just want to go find I want to tap into this node now, go and check the child of this particular node if it correlates with the next element, which will be N. So because it correlates, fine. But you see that the word attribute here is false. Why? Because the initial word that we inserted into our trie is actually band, B-A-N-D, so not B-A-N, right? So because of that, this this node here is not the end of a word. It's not a word, so it is false. And because of that, we are not gonna accept this as a valid word in the tree according to this particular branch, because BAN actually is not the end of a word, does not correlate to a word that is inserted into the trie. So what we do is that we loop out of here. Why? Because we eventually run through each and every letter in our word.an, and we could not find it here. So definitely here it's gonna be a false. So what we wanna do now is to continue here. Why? Because even though BAN evaluate false, dot could be anything. So we just want to come and consider another branch starting from the roots, or emerging from the roots. So considering R now, so let's take R to be the dot. So we are left with an, so we pass an recursively, so it will come and search for an in this remainder of the root now, taking R to be the current node. Previously the current node is root, but because we choose R to be the dot this time around, so the current node is R. So what we want to do is that by passing an into the search function to look for an in the remainder of the of this branch, what we want to do is that we want to try to check into R now, the R node, to see if it has a child A. And because it do have a child A, fine, we tap into A and make A our current node, right? So and we try to check again if the next element, which happen to be the last element in this word that we're trying to search for, if it also exists as a child of N. Fine, it do exist. This is it, because A has two children, T and N, and because N is part of the child, or is one of the child, fine, it do exist. So the next thing that is very crucial to check is if it is the end of a word, that is, if the is word attribute of this particular node is true. And because it is true, fine, we find a word that actually match this pattern or this word .an, and that is RAN. So we return true for this particular search. So at any point in the search, we need to undo two scenarios. So the first scenario is that when we encounter a letter, I mean a letter, not a dot now, but just a normal random lowercase English letter, we proceed to the child of the current node that corresponds with this letter in the tree. And what this place is trying to say is that, imagine we come across a in the process of searching through our word letter by letter, so we come across a we just go look at the current node. Let's say the current node is B. We go look at B and go look at the children, and then we go find the corresponding node that actually corresponds to the letter A. You understand? Don't forget that we use hash map to represent the children, where the children corresponds to the letter, which is A as an alphabet or as a letter, and the value, that's the key, A, and the value is the node. Look at now the node A. So this is B. The key for this particular node will be B, while the corresponding value will be node B, which is a Trie node. So don't forget, a Trie node has two properties: the children property, which represents the children. Look at node A right here, has a children T and a children N. So, and this children is represented by a dictionary, or let me say hash map, whereby we have key value pair, where the key is the letter and the value is the node for that corresponding to that letter. So that's what we're trying to do. Whenever we come across a letter, we try to check the current node, check the children, and find if we can see a key or a child of that current node that corresponds with this letter. So if it exists, then we can explore, we can keep on exploring on. But another scenario is when we encounter a wildcard, and what we want to do is that we want to explore all child node as the dots may match any character. What this place is trying to say is that whenever we encounter a wildcard, that current node, we have to explore all possible children, just like we explore B here and R here. So we explore all the possible children, because any of them could actually be a match for the dots or the wildcard character. Why? Because the wildcard character may match any character at all. So we perform a recursive call for each child node to search for the remainder, and when we find it in one of the child node, no need of going further to search the rest. If you can find the match, fine, it's okay. But if we keep searching through each and every child of the of that particular current node and we could not find it, definitely it does not exist in the trie, and we return false after searching through each and every child in the current node. So that's how we'll be solving this problem, and we'll be going to the code implementation now. Let's go into the code implementation for the insert and search words with wildcard problem. Firstly, we'll be defining our class Trie node that will represent the Trie node, so which is actually for each word we'll be adding into the Trie. Each characters of this word or each letter of this word will be represented as a node in our Trie data structure. So that's what the Trie node is there for, and each of these node we have a children attribute, whereby you could have other node branch out from that particular node. Imagine we are dealing with interface now and internet, and we're trying to add them into a Trie data structure. So we see that they both share the same prefix interface internet, both share the same prefix inter. So and right from that R, which is the ending of the inter, we have net to diverge and face to diverge. What I'm trying to say in essence is that we have internet, right, and we have interface. So we see that they both share the same word up to R. So by the point R, they all diverge. So R now we have two child, so which is F and N. Internet N and interface F. So and that's what children is used to collect this child, so that we can know that this particular node have this number of children and this particular set of children. So let's also define the insert and wildcard, which is another function now that will be helping us to insert words into the Trie and also search for words with wildcards. So first of all, we'll be initializing self. Right, so here we're going to be defining the root node, so which is the node that every other nodes or every other words that we are trying to populate inside the Trie will branch out from. So we're just going to define it as a Trie node as well. So that's it. And then now let's define our insert function now. that will take in a value that we're trying to insert, integer value. Oh, not necessarily it's not a value, it's not taking a word. We're trying to insert a word, which is string, right? So the return will be none. So all of this thing, actually I explained it in the previous video, design a tree. So you see a very much understandable explanation there. So but you can also see such here as well. So we're gonna define the node as self.root. So that's our default node that we have access to, the root node. So okay, then in order to insert word, we're gonna do that character by character or letter by letter. So and for each of them, we want to try to check if C is in the current node, which is by default the root node. So if C is in node.children, so okay, why not let's check if it is not there so we can add it there. So we are trying to insert it letter by letter. So if it is not there, then node.children of C is equals to Trie. So we now add this particular child there, and then node equals to node.children of C, right? So and what we did right here is that if it is not, if this particular node, if this particular character or letter is not a child of the current node, which is the root node by default, then we want to create a Trie node that will represent this particular character, and then we are going to add it as a child of the current node. So now it is a child of the current node, and what we want to do now is that we want to set our current node node to this newly created node, right? So we can traverse into it. So we keep doing that until we finish up, and by then we finish up with each characters or each letters in the word, and by then we can take the last node now and set the is word attribute to true, because that's the end of the word. So now let's proceed to define the search function. Now don't forget this search will be having a wildcard. So self, and we are passing in a word. We are trying to search for a word, right? Okay, and now we'll be having a boolean return that could either be true or false. So what we're gonna do is that similarly we are gonna be first of all defining our node, our current node to be the root node. Self.roots. Now for I, we want to iterate through each word in range of length of word. So we want to iterate through it, and that's why I'm doing like this. So I'm iterating through the index of each string in the word. So and then for high range of length of word, what I want to do is that I want to check if word of I, if it is a wildcard, right? So if it is, then what we now do is that we want to that particular current node, the child or each and every child of this current node, of that particular current node, could be the potential word that we are searching for. Why? Because this is actually a wildcard that actually could represent any character. So we want to iterate through all the child in the current node's children. So and for each of them now, we want to check if we are gonna call the function now. We're gonna call it the search helper. If search helper of I, why? Because fine, we have picked each of the child, or let me say each of the child each of the child of this particular current node to be the dot. We have picked it to be the dot, so we are gonna be sending in I plus 1. Don't forget, I actually represents the index of the current character that we are iterating. So and because we have this character is a dot, so and it could represent any of the child of the current node, so we now are going to pass I plus 1, because now we want to go search for the remainder. Why? Because that current character now is going to be represented by each child in the node. So because it could be any child, so we won't just say this is a dot, we are not going to do anything. No, because it is a dot, it could be a B, it could be a A, it could be a C, it could be any lowercase English letter. So we choose it to be we're gonna consider each and every node, and we're gonna check for the remainder now. So if search helper of this, so we need to pass in our node, so which should be node dot, I mean this particular node, that this particular child node. Now we're passing it into the function. You'll see the reason why we are doing that. Node the children of child, so, and also the word, so that we can index through the word. So now if after iterating through this particular search helper function, if it returns true, it definitely means that the remainder of the characters that follows this white character, imagine we have r dot an, so at least we take dots to be each and every child in the node children, so the remainder an. So if it's actually evaluated true in this particular part, then we just want to return true, because we actually found out the what we are looking for. So but if after iterating through each and every word, it still doesn't each and every node in this current child, it still doesn't return true, then definitely that particular word is not there, so we have to return false, because we tried out all the child or all children in the node or of the node, and it never returned true. So, and that's just it. So what we're gonna do is that, okay, we just want to continue. So this is a condition here for when the index is actually a dot. But if it is not a dot, if it's just a normal lowercase character, we just want to check if it's not a child of the node. Imagine if it's just a normal character like a B, definitely if it is not a child of the node, then I mean if not words of I in node or children is a normal letter, but this letter doesn't match any child in the node, or it doesn't match all children of the node. I mean it doesn't match any child of the current node. If not words of I in, okay, is word, if not word of I in node or children, so we want to return false in this situation, because is a real alphabet, is a real letter, and it is not in the node children, so we have to return true. And eventually if you can iterate true and it doesn't return false, so what we now do is that, okay, we want to set our node to be equals to node dot children children of word of I, right? So why? Because we actually pass check for this condition whereby the word of I is not in, or let me see, if word of I, okay, let's just place it that same way, if not word of I in node of children, so we return false. But in the situation whereby word of I is in node of children, then we are in line. So and what we want to do is just want to set the current node to be that particular node, so that current node to be it. So and if we can keep going on like this, and we do not return a false here, and we don't return a false as well here, definitely we are just gonna return word dot is true, sorry, node dot is true, right? Now return node dot is true. So that is if we can loop through successfully without returning a false. Then that last node, we just want to check if, oh sorry, not is true, is word. We just want to check if it's really a word, so, and it's gonna return true. So if it is, whereas if it is not the end of the word, it's not gonna return true, it's gonna return false. So what I do now is I want to search, we want to also define our helper function now, right? Search helper helper, so which is actually the function that will help us to handle wildcards. So we're gonna be collecting integer high, we're gonna be collecting the node which is a tree node. So we're gonna be collecting the word as well, which is actually just a string, just like how we pass these things right here. So now okay, so one thing you need to know about this search helper is that it's just basically almost the same as the initial search. So just that the search now is not from the beginning of the word, it's actually from a particular index whereby we encounter the wildcard. So and we are searching it right from the node at that particular index, right? So that's just a little difference. So it's just a continuation of the search, just that we are trying to do this search recursively, recursively call this search helper function on each tide. So that's it. And the main reason why we are not just calling it on search itself is because you see that this search initially have just one argument, which is word, apart from the self argument that we do pass into a class method. So you see this word here. So meanwhile, our search helper will be needing more than one argument that will include the index and the node children. So, and because of that, we are just going to pass in this same set of functionality. Okay, let me do something like this. Okay, for j in range of I comma so len of word. And the reason why we are starting from the range of I to len of word is because we just want to start from that remainder point, not necessarily from 0, not from the beginning of the word up to the end, right? And so for j in that, we just are gonna do the same set of things. So I think I'm gonna repeat this whole thing that I have here. Let me start from this. So we just again want to check, because we don't know, we might have multiple wildcard in the in the world. So if it is a wildcard again, so it will be j not I now, it will be j. So it will be j. So if it is, it just be j, right? So and sorry, the here is supposed to be self dot. Why? Because it's a method. So similarly up here it's supposed to be self dot, because it's a method. So if it is a wildcard, then we go through that same process of iteratively recursively calling the self helper on each child until we get the one that is true, otherwise we return false. And but if it is not a wildcard, the same thing that happened in the search will happen. We are gonna check if that particular letter does not exist as a child of this current node, and if it does not, we return false. Otherwise we move on by actually if it is, we return false. If it does not exist as a child in the current node, we return false. So but if it do exist, they want to tap into that particular child, so and tap into the node, so I make it the current node, and we keep doing that on and on until if we can successfully get to the last node. Then we just want to return if that last node is word, if it is actually the end of the word. So and that's really what we want to do throughout. So this is how to solve this problem. And now let's define the parameters we'll be needing. So we have this try, we create this instance of our insert and search wide word. So that's the data structure, the try data structure we have to create. So we've defined the insert method, the search method as well, and the search helper that will help us to search for wide keys. So I mean, it's supposed to search when we encounter a wide key. So we define it and call it the try as an instance of the insert and search word with wildcards. So after that, we try to insert into the try, we insert band and brand, and we try to search for array dot. So let's see if it's gonna work. Right, it returns an error. So it says that this helper function takes in three positional argument, but 4 were given. This is 1, 2, 3. Integer, node, and word. So I think we gave it for start the top high plus 1 node of children and word. Oh, sorry, we are meant to pass in self to it because it's actually a method, and I think that's where the error is coming from. So let's see again. Fine, we have true returned and false returned, which I think is correct, because fine, this first print here we return a true because we have rats and rat matches array dots. So, and this particular slash here should return a true as well, but it returned false. So let's see why it's returned false. Okay, this is the reason why it returned false. I think in the process of copying, we're supposed to be using J. When we copied, we're actually using J and not I. So that's where the problem is coming from. So the current index in this search helper function is J. So fine, we pass in I into the search helper, but this I represents the start of the remainder that I want to iterate through. So J is actually how we iterate through it one by one. So it's supposed to be J, not I. So, but in the process of copying and pasting that I did the other time, I actually I didn't change it to J. So this is true and true. So, and this shows that the problem is that this code is actually correct, and this is how to solve this problem. I'm so sorry for any inefficiency in the teaching. Kindly bear with me tonight, and I really hope you understand anyways. Thank you.